So very good afternoon to all of you, and a big thanks to Dilip and the organizers for inviting Shepherd Color here, and a big thanks from me for being here today for this presentation. So before I get started, if there's two things that I would like you to take away from this presentation, it would be as follows. At the Shepherd Color Company, we are manufacturer of complex inorganic color pigments. We make color. Color is in our DNA, and we love fire. And the reason being, our pigments are made using fire. Complex inorganic color pigments, as you all know, are very inert, and it is because of the processing conditions that make these pigments very inert. My agenda for today is I'm going to be talking about inorganic pigments used as colorants in plastics, why they are used. I'm going to be talking about a lot of different chemistries that are employed in plastics. There are some legacy products that have been used in industry for several decades. I'll also be talking about some newer products, some products that have been developed in the last few years that are constantly pushing the color envelope for inorganic pigments, stretching them into areas where earlier only organic pigments were options. And then I'll talk about some IR reflective properties of certain inorganic pigments. I'd also like to talk about a different concept. Inorganic materials, especially pigments, have technically been used as colorants. But we are finding new uses, and inorganic materials are now being used as functional materials in plastics and other areas as well. So Shepherd Color Company primarily manufactures complex inorganic color pigments, but we have a division of Shepherd Color known as Shepherd Technologies that specializes in functional materials. And there's two applications I'm going to talk about. An inorganic material as a UV absorber, and also inorganic pigment used in LDS applications. So why CICPs? As I said earlier, the processing conditions are very stringent, are very temperature sensitive, because these pigments are fired at very high temperatures, which makes them inert. They are inert to acids and bases, they are inert to solvents. Most of these CICPs, not all of them, have certain UV absorbing properties themselves. So that works very well in certain plastic applications. They are heat resistant and temperature resistant. Most of the CICPs have very broad regulatory approvals. We've all heard about the regulatory issues that are being imposed upon industry, upon all of us. And it is very important for us to stay on top of these things and make sure that our products are compliant. And that is something we can take very seriously at Shepherd Color, and make sure that all our products are compliant. As I said before, we've been pushing the color envelope. We have a very strong R&D department at Shepherd Color and within Shepherd Technologies, and we are constantly trying to find new applications and trying to develop products to meet new applications. I'll talk about IR reflectivity and functional use as well. So why CICPs in plastics? Apart from all the different benefits that I've already spoken of, CICPs offer distinct advantages in plastics. These pigments are easy to disperse. They provide a good option for lead chromate type replacements. Their migration properties are excellent versus certain types of dyes. And I'm not going to read the entire list, but you can see it up on the slide. There's definitely a lot of advantages in using CICPs for applications where durability, weatherability, and heat sensitivity is important. There's a lot of options for colorants in plastics. There's organic pigments, there's dyes, there's inorganic pigments, and each one has its own place. If you can use an organic pigment for your application, you should definitely do that. But as I said, CICPs have certain advantages and satisfy certain requirements. So I'm going to be talking about 15 to 18 different chemistries. I'd like to start with CI pigment black 28, which is a copper chrome black. It's not the most jettest black, but it has very high heat stability. It has all the regulatory approvals that are needed and provides a good option for black. The next category here is Pigment Black 26, a copper, iron, manganese black, a jetter black compared to the CI Pigment Black 28. Both of these blacks have food contact approvals, so they are used in food contact applications. The heat stability of this pigment is less than the previous one. This is heat stable only up to 600 degrees Celsius. Pigment Green 50, very chromatic color, went through some regulatory changes here recently. The products that are offered within this category now have low soluble nickel to satisfy certain REACH requirements in Europe. And there are a couple of companies, including Shepherd Color, that also have nickel and chrome-free products that are used within this category. CI Pigment Green 26, not as chromatic as Pigment Green 50, but has excellent IR reflective properties, because of which it is used extensively in military applications. And all of these pigments, most of these pigments have very good heat stability, so I'm not going to talk about the heat stability for every one of them. CI Pigment Blue 28, which is a cobalt illuminate blue, commonly used for plastic food containers. Excellent heat stability, and there's a range of color within this pigment class. You see this color up on this slide, and on the next slide, you'll see the red shade blue. Again, a very chromatic color, imparts strength during processing and helps with warping in plastics, heat stable up to 800 degrees Celsius, and is one of the excellent options for blues. And these are used in chrome-free applications. The next pigment class is Pigment Blue 36, which is a copper chrome illuminate blue. You see the teal color here, which is very commonly used in engineering polymers. And even with this pigment class, there's a range of colors. The next slide here shows a bright green shade blue, which is also very commonly used in plastics. So these were some of the legacy products, and I'll come back to other colors and other legacy products, but at this point, I'd like to talk about some new innovations in recent years. The Ntp Yellow, the niobium tin pyrochlore, is a patented product. Shepherd Color has a patent on this product. And the rutile tin zinc, the RTZ orange, both of these chemistries combined have really pushed the color envelope in the yellow and orange color spaces where CICPs in the past did not have in existence. And I'll illustrate that with a slide. Let's talk a little bit about the details of both of these pigments before I get to the color envelope. So the Ntp Yellow has a CI pigment classification of Pigment Yellow 227. Heat stability for this pigment is not as high as other CICPs that I've spoken of in the past. The heat stability of this color is greater than 320 degrees Celsius, so not as high as 800 degrees Celsius, but it's still much better compared to other options that are currently being used. So the RTZ orange, a high chroma orange, and is used in blends to move them towards the red shade. Heat stability, again, at greater than 320 degrees Celsius. And both of these products combined have completely transformed the use of inorganic pigments in these color spaces. So as you can see from this slide, in the past, Pigment Brown 24s, which are the workhorse for as far as inorganic pigments are concerned, in this graph, this is where Pigment Brown 24 would be. So I have chromaticity here on the y-axis. On the x-axis, I'm looking at hue, the greener shade to the left and redder shade to the right. The nickel antimony titanates, Pigment Yellow 53, would fall here. We have Pigment Yellow 184, the bismuth vanadates, that would be here, lead chromates that are up here. So this color space here in the middle was definitely being missed by inorganic pigments. The only way to get to that color space was to blend maybe a bismuth vanadate with certain organic pigments. So with the invention and the development of the Ntp Yellow and the RTZ Orange, which are shown where they fall here, what has happened is this. We can now make blends, different blends. So to get to this color space, you have a bismuth vanadate and RTZ blend, a bismuth vanadate NTP blend here, and NTP and RTZ blend here, but you can fill up the entire color space. So inorganic pigments have definitely pushed the color envelope as far as the yellow and orange color spaces go. So if your application requires the use of inorganic pigments, we do have options now that can be used here. Going back to some of the legacy products, Pigment Yellow 53, a green shade yellow. It's an abrasive product, but again, it has extensive use in plastics. Heat stability greater than 800 degrees Celsius. Pigment Brown 24, all of us know about this. This is the workhorse in the plastics industry. A red shade yellow, heat stable up to 800 degrees Celsius. And the chrome antimony titanates are iron-free. Pigment Black 12, iron aluminum titanate, excellent tinting strength, excellent heat stability, definitely less chromatic than Pigment Brown 24, but has its own place in the yellow color space as well. Pigment Brown 33, this is the reddest shade brown in the CICP chemistry and is used to fill in this color space. Pigment Yellow 164, manganese antimony titanates, a great option in thin film PVC applications where free iron is considered detrimental. So again, one of the legacy products. I'm going to shift focus to our IR reflective products. So our Pigment Brown 29 and Green 17 have excellent IR reflective properties. Now again, depending on what your application demands, these are used for outdoor applications. TiO2 is the best IR reflective pigment you can have. But if you want to fill in the darker shades, the blacks and the grays, then blending an IR black would be an excellent option. It has the heat stability and ranges all the way from the blue shade IR black to the darker red shade IR tones, the warmer red shade IR tones, excuse me. So we did a little experiment because obviously the IR reflective pigments, when you measure the total solar reflectance, you see that the total solar reflectance is high. So we did a little experiment in our lab to see what would happen if we had plastic panels. The one on your left here is made using IR reflective black, one of our IR reflective blacks, and the panel on the right is made using a standard black, like a carbon black. So we tried to simulate a condition where we put high energy light on it. And as you can see, over time, the panel on the right starts warping. That's because that panel is absorbing heat, and the panel on the left, the panel made using IR reflective black, is scattering the heat. So definitely a difference here. We tried to relate that to some temperature measurements, and again, there are assumptions built into this calculation. But as you can see, oops, sorry. There we go. A standard black here with a TSR of 5%, and an IR black with a TSR of 25%. So depending on several conditions, and again, as I said, there are some assumptions in this calculation. you can see up to a 10 or 20% temperature difference on the surface. Moving to Pigment Black 30, a very neutral but high tinting strength IR black, heat stable up to greater than 800 degrees Celsius, but used for PVC tinting applications. Within the violet color spaces, Pigment Violet 14 and 16, this is a cobalt violet. It's a high temperature violet, not as high as greater than 800 degrees Celsius that we see with the other pigments, but greater than 600 degrees Celsius, and it's used for toning whites. Pigment Violet 16, the manganese violet, excellent toner again for making whites, a low heat stability, only greater than 290 degrees Celsius, but still works very well in certain applications. So as I had said earlier, CICPs have very good regulatory approvals. There are products that can be used for FDA applications and have food contact approvals. Here's a list of all the different products that I've spoken and the different approvals. Obviously, toy approvals are also important. We have BFR approvals for most of them, AP 89-1 for almost all of them, and then food contact approvals for several of them based on the requirements of the industry. So CICP is definitely a good choice for coloring purposes in plastics, depending on the application. Applications where weatherability, durability, and high heat stability is required. When we look at thermoplastics, I like to categorize them as you would as standard thermoplastics like polypropylene and polyethylene, engineering thermoplastics like polycarbonate, PET, and high-performance thermoplastics like PEEK and PPS. So CICPs are definitely a good option for coloring, but there are other areas, certain functional properties, where inorganic materials also play an important role. And at this point, I'd like to shift focus to UV absorbers. Excellent presentation this morning by the speaker from Chemarc on UV, the whole UV process. I won't spend too much time, just cover some basics, and then talk about a new inorganic UV absorber that Shepherd Technologies is planning to launch in the early part of next year. So what is UV light? The radiation that we get from the sun, 10% of the solar radiation is UV light. And this UV light is electromagnetic radiation that has wavelengths between 100 to 400 nanometers. And there's 3 bands of UV light, the UVA, B, and C. A little better illustrated by this graphic here. UVC, which is the most harmful, fortunately does not reach the Earth's surface. The ozone layer kind of protects us from UVC. The diatomic and diatomic oxygen protects us. UVB, again, even this does not make it to the Earth's surface. But as the ozone layer gets depleted, at some point the UVB, certain parts of the Earth, UVB does hit the Earth's surface. What's of concern here for us is the UVA wavelength. That's the reason we use sunscreens. The UVA hits our skin and can cause skin cancer. And it also affects outdoor applications in plastics and coil and other applications. So UVA is what is of importance here. And there's several mechanisms to protect against UV damage. Again, there's been a good talk about this in the morning. The 3 main mechanisms for protection against UV damage is the use of UV stabilizers. 75% of UV protection in the industry is done by UV stabilizers. There's also UV absorbers. There are several organic UV absorbers out there that are used in the industry. UV quenchers. Now, all of these have different mechanisms. And as discussed in the morning, I won't get into much detail, but the UV stabilizers do not absorb the radiation. When UV light falls on a plastic, we all know about the chalking that happens, the degradation that happens within the polymer itself, and the free radical that is formed. The way UV stabilizers work is they are scavengers. They go and scavenge that free radical and prevent its propagation. And that's how it protects the plastic. UV absorbers, on the other hand, what they do is they absorb the electromagnetic radiation and convert that energy into some other form of energy, and in this case, converts it to heat energy. UV quenchers, kind of like the UV absorbers, they absorb the energy and then dissipate it in the term as heat or as fluorescent or phosphorescent radiation. So each one of these has its advantages and disadvantages, but they need to be used in combination to get the best benefit, again, depending on the application. So a UV absorber is a material that interacts with UV light and converts harmful electromagnetic radiation to some other form of energy, mostly heat. And the examples of UV absorbers are cerium oxide, titanium dioxide, benzotriazoles. As I said earlier, CICPs also absorb a certain amount of UV and can add as protection as well. So when we decided to develop inorganic UV absorber, our scientists sat around the table and they were brainstorming about what would be the properties that would be needed in inorganic UV absorber. And we came up with these 9 different attributes that we thought were important, and we've developed our product around these 9 different attributes. Particle size plays a very important role, and going back to the previous slide, obviously we want a good UV absorber to absorb UV light. So the way particle size comes into play here is organic UV absorbers are typically very fine in the nanoscale. Our inorganic UV absorber are coarser particles. So at the same loading in a polymer, organic UV absorbers tend to do a better job compared to inorganic UV absorbers initially. And that changes over time, and I'll talk more about that here in a little bit. But I just wanted to stress the importance of particle size in the whole process. This slide, just to give you a little example, on the left, we have 3 panels. The first, the one on the top, this one's just clarified polypropylene. This one uses 1% inorganic UV absorber, the inorganic UV absorber that we are going to launch, along with 0.7% of HALs. This here has 0.3% organic UV absorber with 0.7% HALs. So as you can see, there are advantages and disadvantages. The one with the inorganic UV absorber has a little more haze to it. So if you're looking at transparency and clarity, the inorganic UV absorber is not going to perform as well as the organic UV absorber. But if you look at the yellowness, then that we have a better value here with the inorganic UV absorber. So where can inorganic, I think I'm missing a slide here. I thought I had another graph. Where can inorganic UV absorbers be used? Obviously, they can be used in coatings for protection, coil coatings, wood coatings, definitely in plastics for outdoor use, for UV protection. Also finds applications in food packaging, security inks, and laser marking applications as well. And for the best benefit, a UV absorber should be used along with a UV stabilizer, and that would give you the best bang for the buck. Strengths of inorganic UV absorbers when compared with organic UV absorbers. Obviously, these are inorganic, they're non-migratory, non-toxic, have FDA approvals in place, superior heat stability, partially transparent in applications. They definitely have weaknesses too. As I said, at least initially, for the same weight loading, organic UV absorber would have better UV absorbing properties, But over time, the UV absorbers tend to degrade, and that's where the inorganic UV absorbers take over, and they perform better. Inorganic UV absorbers from a price point are going to be more expensive compared to organic UV absorbers. So you've got to balance the pros and cons and find the best application, find the best product for your application. I'd like to talk about an application called laser direct structuring. This is a process